Hello, welcome. In this video we are going to discuss an important theorem. It is related to deformation retract of a topological space. Let D be a deformation retract of a space X. X is the given big space and D is the subspace of the given space. And let X naught be a point of D. X naught is a point which is present present in D, so X naught will be a member of X also. Okay, then pi 1, that is the fundamental group. The fundamental group of the full space X with respect to the point X naught, and the fundamental group of the subspace D, which is the deformation retract of the space X with respect to the point X naught, or with respect to the base point X naught, are isomorphic. In essence, the two spaces, we have two fundamental spaces, one related to the given space and the other related to the subspace, and these two fundamental groups are isomorphic. That means they are same, they behave same. Okay, to prove this, let's take the given space X and the subspace D. Since D is a deformation retract of X, we know that there exists a continuous function, that is the deformation retraction. There exists that the retraction can be taken as H, which is defined from X cross I to X. Then H, there exists H from X cross I to X such that Hx, 0 equal to X. Hx1 is an element of D for X belonging to X, and Hyt equal to Y for all Y belongs to D, belonging to D, and T belongs to I. And we now next we define another function H. H we define from X to D. Let H is defined from X to D denote the that can be defined as a function, and that is actually the one level of H. So it can be called as the special case of, or particular case of, the deformation retraction. We have the deformation retraction H. See, then it has different levels. Various levels are 0 level, from 0th level to the first level, as the value of T varies from 0 to 1 in the closed interval I, we have various levels. So here we take the first level, level 1 of the deformation retraction function H. And then since H is a function, then small h can also be called a function. So H can be defined from X to D. It will be clearly defined from X to D. Why? Because we get that level 1 from this condition, from the second condition actually. So it also says that H of X1 is a member of D, and so since X belongs to X, and this element, the image, belongs to D, this definition is meaningful. So H is defined from X to D. And it has the value, see, as we have seen, it has the value H of X is equal to H X1, where X is an element of X. And next we define H star, and that can be defined from, that is going to be defined from the first fundamental group of the space, whole space X, to the second fundamental group of the subspace. So we define H star. H star is defined from pi 1 x naught to pi 1 dx naught. It is defined as H star of alpha, H star of class alpha, where class alpha is a loop which is present in X, which is based at X naught, based at the point X naught. And then there will be a collection of loops, a set of loops which are homotopy equivalent to alpha, to that particular loop alpha. All those belong to this class. So then class alpha there exists in actually member of this group is class alpha, which corresponds to the particular loop alpha. So we can define H star of class alpha, and it is defined as, corresponding to this alpha, you need actually a member of this class alpha. We need a member of the second group. How do we get that member? That is the question. See, but you know, we there exists a function. There is the function h defined from x to d. Only that can help us to define this. So this can we can define that that class the new loop as h star of class alpha equal to class of h alpha. So here, corresponding to the loop alpha which is present in x, we have the loop h of alpha, because you know, for every loop which is present in x, we have that image or the action of h on that loop. We get the action of h on that loop. That will also be, because h is continuous, since h is continuous, that will also be a loop. Since alpha is a loop, then h alpha will also be a loop. And you can verify that h alpha is a loop which is based at x naught. That can be verified, and thus we can define h star of class alpha equal to class of h alpha, where for every class alpha belonging to the first group. Next, we are going to some important steps. Yeah, step by step we are going to show that this function h star, our ultimate aim is to show that h star is an isomorphism from which is defined from the first group to the second group. So in order to show that it's an isomorphism, first we want to show that h star is well defined. We want to verify whether this definition is okay according to the basic requirements, and then we will show that this h star is it's a homomorphism. It can preserve that operation, group operations, and then we will show that it is one-to-one and then on-to. So these are the steps that we want to go through. So first of all, see, h star, we are going to show that h star is well defined. For that you have to consider, see, two members of two elements of the first group, class alpha and class beta. See, let's take two members, class alpha and class beta of phi1 x naught, with the property that they are equal. See, we also assume that additionally we suppose that class alpha equal to class beta. So we actually, you know, whenever these two members are equal, then you cannot treat them as different. But you know, for this special occasion, in order to show that the function is well defined, you have to for the time being, you have to think that they are equal, and then we will show that the corresponding its images will also is going to be equal. So whenever they are equal, when you consider two different two members, and whenever they are, our aim is to show that whenever they are becoming equal, then the corresponding images are going to be equal in the second group. So if we have, you just assume that class alpha equal to class beta, and then there is a homotopy. You know, if they are equal, we know that there is a homotopy k between alpha and beta, or connecting alpha to beta, or transforming alpha to beta, or from beta to transforming beta to alpha. See, there exists a homotopy. Anyway, there exists a homotopy k between alpha and beta, and satisfying the conditions of the homotopy, or the requirements of homotopy. And since h is continuous, we know that h is continuous, and so you can think about the composition. K is also continuous, and you know by the definition of homotopy, the function k is continuous. So since h is continuous, and then the composition h comma k is that's continuous, and also it's a homotopy. H comma k is a homotopy between the loops h alpha and h beta. So that for that you have that simple verification. For this, first of all, k is homotopy, and so that satisfies the condition k defined from I cross I to x. K is different from I cross I to x, such that k of t0 equal to alpha t, k of k of t0 equal to alpha t, and then k of t1 equal to beta t, and then k of alpha 0s is equal to k of 1s is equal to x naught. So corresponding to this, by applying h, you get that another set of properties, and that these properties actually actually are obeyed by the composition H K. So that's why we say that HK is a homotopy, and this homotopy it transforms H alpha to H beta. Okay, you can verify that. And thus, class of H alpha, you can now think about class of H alpha, thus class of H alpha equal to class of H beta. Thus we get that due to the existence of the HK as the homotopy between H alpha and H beta, we can say that class H alpha equal to class of H beta. That means H star of what actually class of H alpha, according to our definition, we can rewrite that it is H star of class alpha, and now and the second one, class of H beta equal to H star of class beta. Thus we get that H star of class alpha equal to H star of class beta. Hence hence H star is well defined. Now we shall now move to show that H star is a homomorphism. For this also we need to take two different members of the first group, class alpha and class beta, and we shall show that we know that the operation that defined in pi 1 in the fundamental group of X, dot operation, that operation is defined between classes of loops. So we consider that operation class alpha dot class beta, and we know the conversion of that at the level of conversion of this operation which exists at the level of classes of loops, that can be converted into the operation that exists at the level of loops. See, and this conversion or this method we know that that conversion, we have discussed that conversion already. So we are going to apply that conversion here. So hence we can take H star of class alpha dot class beta equal to H star of applying the conversion, it's class of alpha star beta, and this is the operation that exists at the level of loops. So alpha star beta is the composition of loops, and then or the joint of loops, and then we can apply this. H star can be applied to this to obtain the H of we get that this is equal to H of alpha star beta, H of alpha star beta, but H of alpha star beta will be equal to H alpha star H beta, H alpha star H beta equal to H class H alpha. It can be reconverted into it can be then taken back to back to the level of class of loops. So we get that H alpha dot H beta, class of H alpha dot class of H beta, and then we can write finally it as H star of class alpha dot H star of class beta, H star of class alpha dot H star of class beta. Okay. And this dot actually it is the operation that exists in the second fundamental group. Next we shall show that H star is onto. For that, let's take a member of the second fundamental group. Let class gamma be a member of pi 1 dx naught, and then gamma t. See, then we can say that then the gamma t belongs to, okay, gamma t is a loop. Then gamma t is a loop which is based at which is based at the point x naught. Gamma t is a loop which is present in D, entirely present in D. Then H of gamma t, and now you can think about H of gamma t. Since gamma t is entirely in D, the effect of H will be then nothing. Then it will be kept as a constant. It has no effect actually. So when you apply H on gamma t, and you can write it as H of gamma t, equal to H of gamma t, that's H of gamma t. Okay, using that formula. So H of capital H of gamma t. When you apply small h, you can convert into the capital H, capital H of gamma t comma 1, that's equal to gamma t. It's because gamma t is completely present in D. So you can say that H of gamma equal to gamma, therefore class of H gamma equal to class of gamma, and thus therefore H star of gamma, this gamma is a member of, thus gamma is a member of the first group also. pi 1 x x naught also, and you can write that. And you can also get that h star of gamma, that class gamma equal to h class of h gamma equal to class gamma equal to class gamma is a member of pi 1, where class gamma is a member of pi 1 d, pi 1 d x naught. Thus, whenever gamma is a member of whenever there is a member in pi 1 dx naught, then we can obtain a corresponding member in pi 1 x naught, such that its image such that the image of that member in pi 1 x naught equal to the element taken from the second fundamental group, and so h star is onto. This says that this shows that h star is onto. Next, we move to show that h star is 1 to 1. In order to show that h star is 1 to 1, we need to see how do we define that, how do we show that it is 1 to 1. See, for that let us consider class alpha belonging to pi 1 x naught. We define, as for class alpha belonging to pi 1 x naught, we define k of where k, we define k I cross I to x as kt of s is equal to k of t of s is t comma s is equal to h of alpha ts, where ts belonging to I cross I, and then k of t0. Then if this is the definition we accept, based on this definition, then we can write that k of t0 equal to k of h equal to h of alpha t 0 equal to alpha t, and we also have k of t1. In the same expression, if you take k of t1, we get that k of t1 equal to h of alpha t1 equal to h of alpha equal to h alpha of it's h of alpha t1, that's equal to h of alpha t. Okay, and this is, here we have h of alpha t, and that is h of alpha t1 alpha t of 0, that's equal to alpha t, and here we have h of alpha t1 equal to h of alpha t, and it is due to that definition which is followed by or the property of that deformation retraction. When h since h acts as the deformation retraction, and thus we get that is h of alpha t, and then k of 0s is equal to k of 0 is equal to h of alpha 0 yes, it's equal to h of x naught s, that's equal to x naught equal to k of 1s, and therefore k is a homotopy between, thus k is a homotopy between h alpha and alpha, and therefore you know, we can say that here class alpha equal to class of h alpha, and thus class alpha equal to class h alpha. So that means the effect of h on loops is actually nothing there. So whenever we have class alpha, where is class alpha actually present? See, we are taking class alpha belonging to, so for every loop, alpha is an arbitrary loop which is present in x. So for every loop which is present in the first fundamental group, for every member present in the first fundamental group, we have the corresponding loop. For that corresponding loop, we are saying all this. So for that loop, class alpha equal to class of h alpha. And thus, in a similar way, if class beta is another loop present in the given space x, and corresponding class is class beta which is present in the first fundamental group, we get that class beta equal to class of h beta. And now we assume that class h star of class alpha equal to h star of class beta. So for these two, next we proceed with the two members of the first fundamental group. Class alpha and class beta are the two members. Class alpha, we we are taking two members of the first fundamental group, pi 1 x x naught, and they are class alpha and class beta, and also we assume that their images are same. They are in the second fundamental group, that is h star of class alpha equal to h star of class beta. So two elements are taken along with the assumption that h star of class alpha equal to h star of class beta. But h star of class alpha can be easily can be directly converted to h class of h alpha, and also this can be converted to class of h beta. See, class alpha, now this is equal to class of h alpha and this is equal to class of h beta, and therefore moreover due to the relation that exists between class alpha and class of h alpha, we can write that class alpha equal to class of h alpha equal to class of h equal to h star of class alpha and equal to h star of class beta equal to class h beta equal to class beta, and thus we get that class alpha equal to class beta. So whenever class alpha and class beta are two members of the first fundamental group such that their images are equal in the second fundamental group, these two members cannot stand as different. That means they become equal. Automatically they become equal, and thus h star is and thus we get that h star is a 1-to-1, and finally combining all these we can say that h star is an isomorphism. Okay, now see, we have some examples to discuss which is related to the concepts that we have already discussed. Now the examples which tells us or which these examples can shed it can shed light on some important aspects of the fundamental fundamental group, the existence of fundamental group of some special cases of spaces. Okay, so for an annulus, here we are taking the annulus A. So for the annulus A, both its inner and outer circles are deformation retract. See, we have seen that in our discussion, our previous discussion, we have seen that for if you consider an annulus A and it has two boundaries, outer boundary in the outer circle and its inner boundary is in the inner circle, and they can act, both can act as the deformation retract. Both can be the deformation retract of the annulus. And that was in the and now applying the theorem 5.2, the discussions of the theorem 5.2, and we can conclude that it's because of the fact that these are the deformation retract of the annulus. So pi 1 of A, pi 1 of the given space, pi 1 of the annulus A will be isomorphic to the fundamental group of any one of the annulus. See, each annulus is in the form of circle. The annulus are all each deformation retract. See, I'm sorry, that is not the annulus. See, each the annulus which is taken here, it has two boundaries, and these two boundaries can separately act as the deformation retract, and each of these deformation retract is isomorphic. Is homeomorphic to this retract is homeomorphic to the circle S1. These circles both are circles, so they are homeomorphic to the circle S1, the unit circle, and we also know that the fundamental group of the unit circle is isomorphic to Z. So the fundamental group of annulus, which is equal to the fundamental group of deformation retract, the fundamental group of the annulus, that is A, can be equal to the fundamental group of the retract, but this since the retract are homeomorphic to the circle, unit circle, their fundamental group is isomorphic to Z, and therefore the fundamental group of the given space, that is the annulus here, fundamental group of the annulus is isomorphic to Z. So that is the outcome of this discussion. Next we can consider R2. see R2 and then a particular point of R2. R2 is the Euclidean two-dimensional space R2. From that space, one point is going to be removed. See the point set P. Now it consists of all points of R2. So R2 minus R2, from R2 we are removing the point P. That's R2 bar P, R2 minus P, set P consists of all points of R2 except the particular point P. A circle containing now a circle containing P, containing that P in its inner then any circle containing P in its inner region is a deformation retract of it's a deformation retract of R2, R2 given R2 minus P, or P removed from R2. Any circle which contains P in its inner part can act as the deformation retract of the space R2 minus P, so R2 minus set P, and hence the fundamental, but you know that the fundamental group of the circle is isomorphic to Z, the set of integers. And so the fundamental group of the space R2 minus set P is also isomorphic to the group of integers, the additive group of integers. Okay, that's all about this the result, that important result, and it's some examples that come as the outcome of that result that we have discussed. Okay, thank you for listening. Thank you.